Good day, everyone. My name is Hota Gangarao from West Virginia University. I have Drs. Gupta and Liang with me, who will be presenting certain aspects of their modules. Thanks for joining us to learn about polymer composites in terms of the materials that go into these composites, their applications, analysis, design methodologies, long-term responses, and brief discussions on costs. In this slide, I'm presenting the Center for Integration of Composites into Infrastructure map, which highlights the material and component development, including the manufacturing. Secondly, design, field implementation, and evaluation, including durability aspects of composites as a part of our overall research program. And finally, in terms of the technical aspects, development of codes and specifications, including educational issues, are being highlighted in this slide. We have North Carolina State University, Texas A&M, University of Miami as our partners, and we have IAB, that is the Industry Advisory Board, guiding us, and an international site with the IAB chaired by Dr. Vijay Gopu, who is a part of LTRC, that is the Louisiana Transportation Research Center. And we're extremely thankful to LTRC for their help in putting the whole module together. Composites have been evolving and making inroads into marine, aviation, transportation, energy, and other sectors because of their many inherent advantages, which will be discussed briefly today in this module by Dr. Gupta and Liang. However, only recently, composites are finding higher volume usage in infrastructure applications because of diminishing investments and returns, and also discovery of cost-effective solutions and need for 100-year service life has enhanced the use of composites in infrastructure only in the recent past. Few of those examples of cost effectiveness are hydraulic gates, utility poles, lightweight windmill blades because of their high strength to weight ratio, enhanced performance per unit cost. This webinar, we are providing also the educational component. The structure of the course is such that the webinar is divided broadly into 4 modules. The first one being this one, entitled Introduction to Constituents of Composites, including manufacturing and their applications. The second module is going to primarily deal with the durability or the long-term behavior under varying environmental conditions, including moisture, freeze-thaw effects, pH variations, sustained stress like the dead load or the pre-stressing effects coming on to a structure. The third module going to deal with the micromechanical properties determination of composites based on fibers and resins that go into the composites. And the final 4th module will deal with the design of composite members under tension, bending, and compression. Due to time constraints, we will not get into composite system design, especially focusing on joints in these 4 modules, though we have wealth of technical information in the form of slide presentation for the design of composite systems. With this brief introduction, I'm going to pass this presentation to Dr. Gupta, who will be talking about these introduction of composite materials.
My name is Rakesh Gupta, and I will be providing an introduction to fiber-reinforced plastics. The primary constituents of fiber-reinforced plastics are reinforcing fibers and a polymer matrix. This is typically a thermosetting resin. In addition to these two main constituents, one also has fillers and additives. Fillers, such as calcium carbonate, help to lower cost, while additives add functionality. These could be coupling agents, flame retardants, colorants, curing agents, and UV stabilizers. A composite, then, is a heterogeneous combination of two or more materials. In fact, as the name suggests, there are two or more distinct phases which you can see under a microscope. So you have reinforcing elements such as fibers and fillers, and you have binders as resins or polymers. These materials differ in form or composition on a macro scale, and this is easily seen under a light microscope. There exists an interface between these materials, and one often needs a coupling agent to promote adhesion between the fibers and the matrix. With glass fibers, the coupling agent is typically a silane. The role of the two major constituents is, for the fiber, it is bearing the load, and for the resin, it is to transfer load to the fiber network, especially in shear, so that one can have a high interlaminar shear strength. We want to maintain proper fiber orientation, and the resin prevents bunching up of fibers. In addition, a very important role of the matrix is to protect the fiber network from a damaging environment, things such as humidity and high temperature, as well as oxidation. Else, durability suffers. And the nature of the fibers, the matrix, and the geometry of the part to be made dictates the processing conditions of time and temperature. All polymers are made from small molecules called monomers. And when these monomers are combined, you get a linear molecule having a long chain structure. Most thermoplastics, such as high-density polyethylene, which are used for making milk containers, for example, have a linear structure. In addition to a linear structure, one can have branches emanating from the backbone. One can have long branches, and this is what is observed in low-density polyethylene, which is typically used for milk containers. Used for grocery bags. When these long chains get linked together, the branches get linked together by cross-linking arms, they can form a network. And in cured thermosets, such as vinyl ester, polyester, and epoxy, you have a network structure. An example of a network structure is rubber. Natural rubber is a linear molecule. It is cross-linked with sulfur, and the process is called vulcanization. That makes rubber useful. The structure that one observes, linear, branched, or network, depends on the starting materials, the reactor conditions, and the presence or absence of any catalyst. Within a polymer, one talks about monomers. Two monomers combine to give you a dimer. A dimer combines with another monomer to give you a trimer, and as the process continues, you get an oligomer. when there are enough mers that react with each other, you get a polymer. In a polymer, one can identify a repeat unit, which could be the monomer, or it could be a molecule which has some atoms missing when compared to the monomer. The world of polymers is divided into thermoplastics and thermosets. Thermoplastics are large molecules which have already been made in a reactor, and then they are used to make useful products. Thermosets, when one uses thermosets, one begins with small molecules which have a low viscosity. Once the thermosets are formed, they do not flow upon heating because the liquid resin is cured and becomes rigid. The other characteristics of thermosets are that the cured polymer is less temperature sensitive than thermoplastics. It will not soften upon heating. The network structure exists throughout the part, and you have thermal stability so that the polymer does not flow upon heating. However, it can degrade at high temperatures. The advantages of a thermoset over a thermoplastic is that one deals with low viscosity materials. As a result, one gets good fiber wet out, which means that there's good adhesion between the resin and the fibers, which results in a low void content. There's excellent thermal stability once the material is polymerized, and the material is chemically resistant and creep resistant. Thermosets have some downsides as well. They are brittle, which means there's a low elongation at break. With thermoplastics, one begins with a large molecule, and one heats it, it melts fairly quickly. You make a part, you cool it, it solidifies, and the process is over relatively quickly. With thermosets, there can be a long fabrication time, especially when one deals with epoxies. There can be a limited storage life at room temperature before curing, because one uses curing agents such as peroxides. Even at low temperatures, they can decompose and curing can begin, so the shelf life is limited. Thermosets are non-recyclable by standard techniques because they typically will contain fibers and fillers. The molding of the part is the mold is in the shape of the final part, which means that once we have made the part, we cannot change it later on, so these materials are not post-formable. The most common thermosets are polyesters, epoxies, and vinyl esters. The polyester that's used is typically it's an unsaturated polyester, which means that there are double bonds present. Common materials which give us an unsaturated polymer, a polyester, would be maleic acid reacted with ethylene glycol. That has a double bond in the backbone, and you can see that just above the words where it says unsaturated acid, it is CH double bond CH, and that double bond is the site of cross-linking. Other high-performance materials are epoxies. They are made by reacting bisphenol A and epichlorohydrin that gives a three-member epoxide group at the two ends of the molecules. One can react the epoxide groups with acrylic or methacrylic acid, and that gives a vinyl ester. And if you look at the vinyl ester molecule shown over here, it has double bonds at the two ends. These double bonds are then the sites for cross-linking. Polyesters and vinyl esters are cured by dissolving the prepolymer in styrene, followed by cross-linking with the peroxide. Epoxies are cured using amines. So you start with monomers, you get a prepolymer, you then cross-link it with either a peroxide or an amine, and the result is that you start getting molecules which have branches emanating from the backbone. The glass transition temperature, which I'm going to talk about in just a moment, rises as curing proceeds. If the glass transition temperature reaches the cure temperature, the reaction stops, and this is called vitrification. If the temperature is raised, curing is resumed. Typically one uses a temperature at which the cure goes to completion. And once it is completed, the material is typically used at a temperature below the glass transition temperature. If one goes to a temperature above the glass transition temperature, the material is rubbery. For a given reactant concentration, the extent of cure, or meaning how close the material is to being fully cured, depends on time and temperature. Also note that polyesters and vinyl esters typically shrink on curing. What the graph shows us is that if the temperature for cure is low, the glass transition temperature is reached and reaction stops, leading to a partially cured part. If the cure temperature is too high, the polymer cures but then degrades. If the time of curing is too short, curing may not be complete. And if the time is curing is too long, we get a process which is uneconomical. Typically, for epoxies, it takes 60 minutes to several days for complete curing, whereas for vinyl esters and polyesters, it takes 30 minutes to an hour. For urethanes, one can get curing in a matter of seconds. If the behavior of polymers depends on the temperature at which one is examining the behavior. At low temperatures, there is very little molecular motion and the material is glassy, which means it is brittle and rigid. Under these conditions, if one tries to deform the polymer, one stretches primary chemical bonds. This takes a lot of effort, and the material, therefore, is stiff. Above the glass transition temperature, molecular motion begins, and parts of the polymer can uncoil or unwind when we try to deform it. As a result, the material is softer. We call it rubbery. For composites use, we use a temperature which is less than the glass transition temperature. This inhibits creep. However, we can enhance toughness by adding elastomers to the resin used in the formation of thermosets. Turning our attention now to the other component in a composite, which are fibers. The most common kinds of fibers are glass fibers. And the glass fibers can be of different kinds. They are designated as E-glass, S-glass, or AR glass. E-glass are the most common ones. E stands for electrical. These have high electrical insulation, low susceptibility to moisture, and very good strength. These are most commonly used because they are also the lowest cost glass fibers. S-glass fibers have high strength, and the S stands for strength. The AR have improved chemical resistance, and AR stands for alkali resistance. And these S-glass and AR differ from E-glass because of a difference in chemical composition. Glass fibers have many advantages, particularly low cost, high strength, high chemical resistance, resistant to fatigue, and have good insulation properties. They also have some limitations, low tensile modulus, high specific gravity compared to carbon fibers. They're not as resistant to abrasion while handling, and they have high hardness. Glass fibers come in different forms. One can have a spool of, we can have a group of untwisted strands, which is called a roving. A mat can contain uncured resin, and then one can make fabrics from rovings. And these different forms are relevant for different composite manufacturing operations. The other major kind of fibers used are carbon fibers. Here one typically starts with a textile fiber and removes all but carbon atoms by heat treatment. And the textile fiber one uses is pan or polyacrylonitrile. It offers good strength and high modulus, also excellent compression strength. One can get even higher moduli if one uses pitch fibers, and the pitch could be typically derived from petroleum asphaltenes. And here one can go to a modulus of up to 140 MSI. The coefficient of thermal expansion of these materials can be relatively low, and this offers many advantages. The major advantages of carbon fibers are high tensile strength to weight, very low coefficient of thermal expansion, and high fatigue strength. The major disadvantage is high cost compared to carbon fibers, so compared to glass fibers. In addition, they can be brittle and have low impact resistance, and being made of carbon, they're electrically conductive. And as in the case of glass fibers, they can be in the form of a roving or tow in fabrics and as a mat. It is often advantageous to use a preform because it gives fabrication advantages, especially in operations such as resin transfer molding. So we do not use fiber rovings. We use a preform mat, which is an assembly of reinforcing fibers already shaped and oriented in the form needed and placed in a mold. These can be highly permeable, so they allow resin to be infused, and they have a high degree of structural integrity. The disadvantage is that they can have poor stiffness, limited strength, and the volume fractions of the fiber is not as high as one can get if one used rovings. The rovings that one can employ can have different architectures. If all the fibers are aligned in the same direction, we have a unidirectional roving. And what is shown in the figure is unidirectional rovings have parallel filaments which are held together by stitches using a yarn. Since they're all pointed in the same direction, the stiffness and strength can be very high in the filament direction. However, the mechanical properties perpendicular to the axis of the fibers are not as high as those along the axis. Also, one can have bunching of the fibers, which is what we call fiber wash. And clearly, the properties are anisotropic. They depend on the direction. And the properties can be poor in a direction perpendicular to the axis direction. To address the anisotropic properties, one can use two-dimensional woven fabrics. And the weaves can be classified as open or closed, depending on the spacing between the fibers. These will give a balanced properties in the plane of the fabric, good impact resistance, and good conformability. However, one can see just by moving our hands on top of the fabric that there's undulation, and there can be difficulties in trimming or handling these fabrics. So now we've talked about the resin, we've talked about the reinforcement. The two come together in a manufacturing operation. The simplest manufacturing operation for making composites is hand layup. Here we put reinforcement into an open mold. You add resin, you compress the two with a roller, and then you heat the material to initiate curing. A more complex operation is RTM, or resin transfer molding. Here you put a preform in a mold, you close the mold, inject uncured polymer, and heat to cure. The third common important operation is compression molding. Here you use a sheet molding compound, which is a sheet of fiber and resin. You put it in a preheated mold, you close the mold and apply pressure, and this results in curing. A continuous operation is pultrusion. Here one starts with unidirectional glass fibers and continuous strand mat. It goes into a resin bath. You pick up the resin. The material then goes into a preformer where excess resin is squeezed out, and then the resin infused reinforcement goes into a heated die. Within the die, curing takes place, and what emerges from the die is a solid part. It's pulled by a device, and then what emerges from the device is then cut to the appropriate size. And the quality of the parts depends on fiber wet out, extent of cure, which depends on the curing temperature and time. The void ratio depends on the processing conditions. Higher the void ratio, the worse the quality. And all of these then determine the quality of the part. So to conclude this introduction to composites, the composite properties depend upon both the reinforcement and the resin, and they depend on the processing conditions. One of the advantages of the appropriate choice of polymer and reinforcement is that we can meet design requirements. We typically do not wish to over-design a part because that then adds cost, but we have so many variables that we can address the needed requirements for mechanical properties and durability.
Okay, this is Ray. I will give a broad brush on some of the FRP applications. The Hota, in the introduction of the webinar series, has briefly introduced the NSF-IUCRC, the Center for Integration of Composite into Infrastructure, in short, CICI. The mission of the CICI is to adopt polymer composites and innovative construction materials for infrastructure applications. These applications include, but are not limited to, the following: highway, railway, waterway applications, buildings, housing, pipelines, utilities, and energy industries. As you know, in order for a new material into construction, we also need standards, specifications, and codes, which has been a focal area in the CICI upon establishment. More applications beyond what we covered here today can be found in the book chapter contributed by the Hota and me in chapter 32 in a book, Applied Plastic Engineering Handbook, to be released in January 2024. This slide shows FRP Composite Wikigate was manufactured by the vacuum assisted infusion process. The top left picture shows the mold, and in the center of the top shows assembly of the sandwich coal wrapped with FRP glass fabric to have the shape of the product, and followed by the resin infusion process as illustrated by the bottom center picture. Then followed by the demolding of the product on the left, and further by some fabrications, including the painting, assemble some fixtures onto the gate, and then ready to be used. This bottom process is a batch operation. This is a protrusion process. Protrusion process is a continuous automatic process. So this slide shows the composite sandwich panel is being manufactured using the protrusion process. And the lab process, including all the fabric, go to a bath and into the die and poured by the puller to a certain length. The cutter saw will cut the panels into a given length. And from the left bottom picture shows final product, and with tonga and groove joints. So that's a modular panel design. This is a 4-foot module, but you can assemble into 8-foot, and then versus to 12 and 16-foot panels. WVU Construct Facility Center and the leadership of Professor Hota Gangarao pioneered FRP on the research and development in 1987 with NSF sponsored a research workshop entitled FRP for Construction. At the workshop, research topics, research challenges, and research gaps to bring the FRP into practice were identified, followed by the extensive exploration in many aspects, including durability and also a large number of demonstration projects in many states. This booklet in this slide and titled Fiber Reinforced Polymer Composite Bridges of West Virginia, compiled and published by U.S. Department of Transportation Federal Highway Administration in collaboration with West Virginia Department of Transportation in 2001. A newer version was released by ACMA, American Manufacturers of Composite Association, in June 2015. Both electronic versions are available upon request. This booklet highlighted the FRP composite in different forms applications. And for example, an FRP rebar as a reinforcement, FRP deck to replace the concrete deck, and also FRP wraps to retrofit existing constructed facilities, and also the full complete composite vehicle bridges. And a total of 35 case studies are collected in this booklet. On the left picture shows the market straight bridge in Wheeling, and highlighting FRP composite deck are being used here in lieu of the original or rotted concrete deck. This picture shows the bridge deck in different generation, or you can say in different evolutions from about a span of about 10 years. And there are 5 designs here. The first one on the top left is a double trapezoid, and the second one is a revised version of trapezoid. Third one is a 8 inches high profile lightweight composite bridge deck. And the fourth one is a 4 inches and a low profile bridge deck. And the fifth one is already, we have seen it from the protrusion case, is a sandwich panel modular design deck panels. And from generation 1 to generation 4, we can see a shape change. Actually, there are lots of other performance change as well. As you know, typically FRP deck in weight is about 1/6 of a concrete deck. And from generation 1 to 4, the weight per unit area has been reduced to half. Instead, the performance has been 4 times higher from the generation 1 to generation 4. Similarly, the cost-wise, cost has been reduced only 1/3 of the original version of the bridge deck. So all these advances, advancements were accomplished by adoption of efficient design and advanced manufacturing at higher productivity and along with higher joint efficiency. This slide shows a lightweight, non-corrosive FRP rebars are widely used as a reinforcement to replace steel rebars for highway bridges and roadways. And top left picture shows McKinney-Weil Bridge in West Virginia is a 180 feet long, built in 1996. It is the first case to use FRP rebar on a bridge deck in US. Currently is still in good condition. This slide shows FRP wraps for retrofitting existing bridges. Applying banded type of FRP wraps to restore, retrofit, or repair or strengthening the existing bridge has been proven an effective way to make existing structures to last another long, several tens of years. FRP wrap technologies include design aspects, installation procedures have been very well developed. And the effectiveness of the retrofitting can be easily established by conducting load capacity before and after doing the rehab. So this picture shows 3 bridges are being retrofit. In the Turnpike Bridge to retrofit the column, and the Denzel Mill Bridge retrofit the column as well, and also to the Obikisha bridges to retrofit the bridge deck. And really by adopting this kind of innovation technologies has saved millions of dollars for West Virginia Department of Transportation. This slide simply shows FRP shapes, and deck panels are being used to construct World Trade Center area FRP pedestrian bridge over 9th Street in New York City. Next example is the retrofitting of the railroad timber bridges using FRP wraps in Moorfield, West Virginia. FRP wraps were first used to retrofit railway timber bridges in 2000. because of their proven success in 2000, so in 2020, 2010, another 35 bridges, railway bridges, were retrofitted using FRP wraps, as the picture shows here. FRP powering is another major applications. This including FRP sheet powering and FRP pipe powering. On the left, original timber boardwalk was damaged by Hurricane Sandy back in 2013. Then in the picture, the top center and also left bottom shows those boardwalks are restored using the FRP sheet piles by the creative protrusion, which is our CRCR member. On the right, bottom picture shows pipe powering being tested in the West Virginia University lab. This shows a 10-foot wide, 70 feet long GFRP composite Patterson bridge was being constructed using a WVU structure truss member, individual truss member, and with FRP deck. And the WVU also evaluated several other bridges. All these efforts not only lead to the use of FRP Patterson bridges in an economic and durable manner, also help different clients located in rural and urban areas. But also generate inputs to revise and refine US AASHTO design specifications for FRP Patterson bridges. The bottom right picture is the world's largest or longest protruded FRP bridge by creative protrusion that was constructed in Bermuda. Let's move on to the waterway applications. In June 2020, working group 191, composite for hydraulic structures under the World Association Waterborne Transportation Infrastructure, as known as PRANC, released design guides or case studies composite for hydraulic structures, as you see here, the book cover, showcasing FRP composite for a number of applications, including design considerations and case studies, success stories. And in the center of the slide shows a movable vehicle bridge and using FRP structures in Muiden, Netherlands. For the locket gate applications, engineers and designers in Netherlands are leading the way. This picture shows the world's largest FRP locket gates in Wilhelmina Canal, Netherlands. It was designed by the Infraco in cooperation with a size about 20 feet in width, 43 feet in height, using materials glass fiber and polyester with vacuum assisted resin transfer molding. A design life is over 100 years. The initial cost of the FRP structure is lower than a conventional structure. It was installed in 2014, still performing outstandingly so far. This picture shows a WVU case studies using off-shelf FRP products to construct recess panel in replacement of steel panels, which are costly, heavy, and easily clogged. And this product was installed in 2016. Okay, now what we are looking at is a volt receiving application, a retrofit of corroded steel power bridge, steel edge power bridge in West Virginia, Huntington. And the FRP approach was used to transform the obsolete bridge into a new bridge, or a bridge with new life. The right pictures shows some details during the retrofitting, but in short, and we are able to bring the load capacity back to original design only at 25% of traditional repair cost with use of composite shell and wrapped around with FRP wraps and then filled with the concrete. So, and this really demonstrates composite is an enabling technology. We see the FRP wicket gate again, just with more details in field implementation. And U.S. Army Corps engineers who manage the United States waterways has ordered 220 wicket gates, FRP wicket gates. Right now, as of today, 114 composite wicket gates being delivered by the creative protrusion. So this case really highlights successful showcasing fundamental and applied research leading to field implementation with composite advantages, including innovation, design, flexibility, and non-corrosiveness and durability. Now we are move on to the utility poles, which is a multi-billion business, even annual replacement market and a new market also about several billion-dollar business. And on the right, you see FRP poles being tested in a structure lab. So anyway, FRP poles has been receiving more attention from the utility company due to their advantages over the wood, steel, and the concrete. But in general, people will believe FRP poles will burn under fire. Since wildfires pose a threat for FRP poles, and sponsored by the Electric Power Research Institute, WVU researchers has conducted research on fire performance of FRP poles extensively. We have developed a frame test that simulate the wildfire that gives about 1,000 Celsius constantly. And we subject the FRP poles to the flame exposure under 1 minute, 2 minutes, 3 minutes. In conclusion, our research, FRP poles, especially with use of intermittent coating, are able to survive general wildfire, while use of sleeve protection methods will provide full protection of the FRP poles. All this help utility companies to use FRP composite poles with confidence. As you know, let's look at a few innovative new applications for FRP materials. The EV, electric vehicle, have been growing every day and in their market share. Access to charging stations has been a concern for many EV users. The solar charging stations constructed using FRP shapes and decks panels or profiles offer a great solution for rural, remote, and suburban area, as highlighted in this slides. As you know, wide blades for windmill have been a major driving factor for the composite growth for the past 15 years. Hydrogen storage tanks right now has been another driving factor for composite growth. This picture shows vehicle vertical taking off and landing flying aircraft, or simply we call air taxi. ACMA has a dedicated working group on this. This application is regarded to have a huge potential to be one of the major driver for the future composite growth. It is expected a multi-billion business in this topic alone. So in conclusion, advanced composite advantages of composite over conventional materials and a harsh environment, including weight-sensitive applications, include design flexibility, non-corrosion, high performance per unit weight, and durability. Universities, in collaboration with government and industries, has made major strides with FRP applications. Based on a limited in-service data, in-service FRP composite systems for infrastructure applications are leading to longer service life, lower initial and lifecycle cost. With code acceptance, FRP composite still became an integral part of infrastructure applications, including retrofit of aging structures at 15 to 30% of conventional repair cost. Society or our community will benefit from the increased use of reliable and durable composite materials with low maintenance, longer service life, and green products. Here I put a few references for further reading, and if you have any questions, please contact any of us. Thank you very much for your attention.